Well, good afternoon, everyone. This is Burke Callwhite. I'm the Executive Director of the American Academy of Environmental Engineers and Scientists, and we are your hosts for this webinar today. I want to thank everyone for tuning in and filling you in on exactly what we're doing here. This is about the 10th installment of our based on our environmental engineering, excellence in environmental engineering and science conference that we have every year. We have multiple presentations which we've converted to webinar format for this series. The most important thing here is these are all what we call our grand prize winners, of which we have a 10 overall, and so anyone who wins a grand prize has really done their homework and has a highly meritorious, award-winning kind of presentation that they've done for us. And the one today is no exception. Our sponsoring firm is Hydrogeologic, Inc., and they have provided us with actually 2 grand prize winners in this year's competition. And today we have 3 different speakers to go through the various aspects of the presentation. First speaker is Bill Collins, who is the Base Realignment and Closure Environment Coordinator responsible for overall Fort Ord environmental cleanup. And it's a hazardous waste and munitions cleanup within about 28,000 acres, so there's quite a lot of ground to cover there. Bill's worked with the U.S. Fish and Wildlife Service and the California Department of Fish and Wildlife to develop biological opinions and options for species and habitat protection during remediation. Bill holds a Bachelor of Sciences in Natural Resources Management. Our second speaker is Roy Evans, who is a principal engineer at Hydrogeologic with over 40 years' experience in the environmental field. He has successfully completed projects that involve site cleanup, environmental characterization, groundwater remediation systems and optimization, facility demolition, and surface and groundwater flow and transport modeling. Roy has received commendation for his work at sites in California from the California Regional Water Quality Control Board and the U.S. Marine Corps. Our third speaker is Varut Govardhan, who is Vice President of Research and Development and a modeling expert with over 30 years of experience in water resources and environmental engineering. He has managed and provided technical leadership for projects in the U.S. and overseas related to water resources, nuclear waste disposal, and environmental remediation, including the application of hydrogeologic PBMO product and process at the former Fort Ord project. He's also developed many theoretical models and computer codes, including exposure and risk assessment models to support EPA's hazardous and industrial waste programs. So with that being the case, let me hand this over to Bill and let him open up the program for us.
Thank you, Burke, and welcome. I'm looking forward to this presentation. It's a beautiful sunny day here in California. As Burke said, my name is Bill Collins. I'm the environmental coordinator for the Fort Ord Base Realignment and Closure Office. The project team of the presentation today is the Fort Ord BRAC Office, the U.S. Corps of Engineers Sacramento District, the California Department of Toxic Substances Control, California Regional Water Quality Control Board, EPA Region 9, as well as one of the stakeholders who owns the property is University of California, Santa Cruz, and of course Hydrogeologic, Inc., who was awarded this grand prize. So I'm going to give you a little background on the Fort Ord project. Fort Ord began in 1917 as Army training base and closed in 1994. The 28,000-acre installation primarily used for training soldiers to prepare for the previous world wars, as well as training for an infantry use. The area that we're talking about today is Fritchie Army Airfield. It's a piece of property located on the northern portion of the base. It was constructed in the 1960s as an airport. In 1990, Fort Ord was placed on the National Priorities List and became a Superfund site. Therefore, all of the cleanup operations done by the Army on the base are overseen by the EPA, California Department of Toxic Substances Control, as well as the Regional Water Quality Control Board. Again, the base was closed in 1994 under the Base Realignment and Closure Act. One of the challenges that we have on our cleanup program here is to deal with federally and state-listed plant and animal species that occur throughout the base. It adds a little more complexity to the project when you have to avoid and minimize impacts to these species during the cleanup project. The Army's performing these base cleanup projects to support the reuse of the installation. It's primarily 19,000 acres has already been transferred to local jurisdictions, as well as the Bureau of Land Management as part of the Fort Ord National Monument. There are other educational facilities on the base other than UCSC. One of the largest is the University of California, Monterey Bay, as well as other private developments that are occurring throughout the other jurisdictions in the City of Monterey, City of Seaside, City of Marina, as well as Monterey County. As I mentioned, the remediation efforts have to meet the requirements of the biological opinions issued by the U.S. Fish and Wildlife Service to ensure that we mitigate the impacts caused by the cleanup activities. So in 2003, the Army began awarding performance-based contracts. These are fixed price contracts to help accelerate cleanup activities and also to reduce costs. The contracts for Fort Ord are awarded through the Corps of Engineers office in Sacramento, California. This is the one and only PBR contract that's been awarded at Fort Ord, and it was very successful because of the optimization to the contract. It helped increase the efficiency of the cleanup and resulted in cost savings. So at this time, I've turned the presentation over to Roy Evans with HGL Inc. Roy?
Thanks, Bill. The slide that you're looking at now gives you a close-up picture of Operable Unit 1, which was the operable unit HGL was responsible for. You can see to the lower right-hand slide, which is marked as Marina Municipal Airport. That's its current name. That is the former Fritchie Army Airfield. The little pink circle due west of that is the source area. Every military airfield, as well as every civilian airfield, then and now, has to practice putting out the airplane fires in the event of emergencies. And the typically way they do that is to clear out an area, a couple football fields in diameter or thereabouts. They'll burn them up 6 to 12 inches on the edges. They'll put in a dead airplane carcass in there, and then they'll light all-spec fuel or other ignitable sources and put it out. So that's the type of operation that they conducted there at Fort Ord from 1962 to 1985 when the airfield ceased operation, or the military training rather, ceased operation. Of course, whatever doesn't burn up when you do that infiltrates into the ground, and that led to the groundwater contamination plume that extended from the pink circle there north and then to the northwest. The dashed lines and the green line on the off-post part of the base show the maximum extent of the study area, not necessarily the plume. The plume generally followed along the center line of that shape that you see there and moved to the north-northwest, probably maybe 50 to 200 feet wide at its biggest parts. The UCS Fort Ord Natural Reserve encompasses the dark gray and some of the light gray area that you see within there. I'll refer to that for shorthand as FONER, probably out of habit later in the talk. But in particular, the dark areas are home and habitat to some of this protected species that Bill mentioned earlier in his presentation. And the light areas in the gray are non-native or invasive grasslands and potential sources of invasive species. They'll come into play a little bit later too. Hydrologically and hydrogeologically, Fort Ord's underlain by 4 permeable aquifers separated by 3 aquitards. Operable Unit 1 was concerned with the uppermost aquifer referred to as the A aquifer. A aquifer in this OU1 area is sandy, very permeable. The plume tends to sink to the north. If you look at the little cartoon to the right of the slide, you'll see the FDA is the fire drill area, which was the source area. And the depth to groundwater was typically 50 to 90 feet, saturated plume thickness anywhere from 35 to 50 feet. And as you can see, as it heads to the north, you get a body of, a layer rather, of clean water over above the top of the contamination. You're only about a mile and a half from the Pacific Ocean in here in Marina State Beach. As work sites go, it's pretty great to work at a nature reserve by the beach. The source soils at the fire draining area were removed in 1987 as part, shortly after the initial environmental investigations began in 1984. So HGL's task was a fairly aggressive cleanup schedule under our performance-based contract. We were striving to hit cleanup targets and embark on site closure within 6 years. There were 10 VOC contaminants arising from the fire training activities. TCE was the principal contaminant and that it lasted the longest. All the others had pretty much met their targets about 3 or 4 years after we got started. And TCE footprint encompassed the maximum extents of the other contaminants. A record of decision was developed between the Army and the agencies that Bill mentioned that established soil removal, which had already been done in 1987 as that option, and the ROD was signed in 1995. It also established pump and treat as the selected remedy for cleaning up the groundwater using activated carbon as your treatment vehicle. And groundwater cleanup targets were established as either the MCLs or risk-based levels. Now remember, this is 1984, investigations beginning in 1995 for the ROD, so emerging contaminants such as perfluorooctanoic acid and perfluorooctane sulfonate, and I'll avoid that mouthful by referring to them as PFOA and PFOS hereafter, were not on anybody's radar and were therefore not included in the ROD. So embarking on our cleanup schedule with all intents of being aggressive and fast, we just ran into some initial problems. The red and yellow checked area that you see there within the dark part of the background was the understanding of the initial plume extent when we started late in 2003. However, as we developed additional site investigations and performed some vertical profiling of the aquifer to facilitate the design of the cleanup system and the expansion of the pump and treat system, we discovered that the plume had in fact migrated more to the northwest and even beyond former Fort Ord's property boundary and onto private property there at the Armstrong Ranch. So this certainly created a lot of headaches for everybody and changed our priorities pretty quickly, and it's what we had to do. So the major challenges we faced right off then were the plume extent had not been fully defined, and we needed to halt the off-post migration as quickly as possible. As Bill mentioned, two of the species that were out there, they're Monterey spineflower and sandgilia, which are widespread throughout the Aqua 1 area, and they're all part of the FONR system. Now, the FONR is owned and managed by the University of California, Santa Cruz, and they use this as a big outdoor research laboratory for examining impacts and conducting outdoor experiments on the survivability and factors affecting the rare plant species as well as the habitat that hosts them. So the last thing they wanted to see was a lot of remediation efforts such as wells and pipelines and roads being basically constructed through their laboratory. We also had to deal with the potential presence of a California tiger salamander. These were species there that basically if we saw them we had to stop work and get a qualified biologist such as Bill or one of our subcontractors to come out and move the little fella. The biological opinions that Bill helped develop and the habitat management plans dictated that we could not disturb the habitat area or the plants between November and May. So this gave us a somewhat truncated work season to construct wells or pipelines or roads. And finally, and critically important to the performance and from a cost standpoint, was we could have no net impact to the plant populations at the end of the remediation effort. If it turned out that we impacted by decreasing those populations to an unacceptable extent, then we would be responsible under this fixed price contract for restoring those habitats. And that would have run into well into the six figures of extra cost. Another feature that we had to consider was Operable Unit 1 is just one of 4 operable groundwater units underway at former Fort Ord, and immediately to our west was the carbon tetrachloride operable unit. there's a plume there that was migrating parallel to the TCE OU1 plume. And this being a pump and treat operation, we had to be careful to make sure that our distortion of the groundwater flow field as part of our remediation didn't transfer over and impact the path of the carbon tetrachloride plume and complicate that cleanup effort. The contract constraints, as I mentioned, this was a fixed price job, and we had an aggressive cleanup target. So the solutions that we came up with to get this job done fell into 4 general categories: phasing the construction, natural resource management protection, and optimization and an exit strategy for PFOS. Let me talk a bit more about those items. This slide shows the eventual extension of the Fort Ord groundwater treatment system that was established in 1988. Down in the lower right, down here, you can see the 2 wells that were initially established. An initial GAC system was established here in the former source area, and this system had a capacity of roughly 20 gallons a minute. Phasing construction, as I mentioned, we had originally planned to construct extraction wells in this region here in the central, but that was before we realized how far the plume went. We revised our design and schedule, and as quickly as we could put in 4 hydraulic control extraction wells along the northwest boundary, as shown here in the purple labels. We got these in the ground and operating in July of 2006. In the next construction season, we moved along the axis of plume migration and established these 4 wells here, extraction wells along the spine of the plume to accelerate the overall cleanup. Later, and I'll talk about this as part of the optimization, we converted this monitoring well here into an extraction well, added this extra piece of pipeline, and brought a 5th extraction well online. So in summary, we wound up with 4 extraction wells on the boundary, 4 along the plume axis, subsequently became 5. We had 2 infiltration trenches and 2 injection well trenches. Those are these green bars that you see here for infiltration and 2 injection wells here on the west. We used our groundwater 3-dimensional modeling that we had put together to help design the plume extraction system to locate these reinsertions of treated water into the aquifer in a manner that helped improve hydraulic performance and capture of the plume itself. The overall treatment system capacity we built was for 200 gallons a minute. For natural resource protection, a key part of it was constructing pre-construction plant population surveys. We used these surveys and trained biologists to go out each spring when the plants are blooming and map and locate extensive populations in key habitat areas. We were then able, with that knowledge, to design the system insofar as we could to place wells and pipelines in areas that would not impact the plants. Seed bank preservation was also a method that worked very well for us. Both spineflower and sanguilia, their seed bank, as they bloom each year, tends to be preserved in the upper few inches of the soil. So wherever we came to a new well site or had to construct a road, we scraped and topped the 6 inches of the soil. We then put that off to the side, and as a final part of our restoration at each action, we replaced that top 6 inches back roughly where it had been. And as the picture on the right illustrates, in places where we just couldn't avoid going through sensitive habitat, we used mats to lay down onto the soils and help mitigate the impacts to the underlying flowers. We were very diligent about making sure the drilling crews, survey crews, and every sampler in the field was aware of the habitat restrictions and what rare and protected species look like. You see a California tiger salamander there on the right. We maintained good biological oversight. We had qualified personnel on site anytime we were in a particularly sensitive area or a particularly sensitive operation. And if they weren't on site, they were nearby and on call 24/7. We also coordinated closely with the University of California, Santa Cruz. That Bill mentioned, they're the property owner, and they are the ones conducting the basically habitat and species experiments throughout the perpetuity there. And we talked with them about where we would locate infrastructure. And one of their concerns, if you remember back when I was pointing out the light and gray shaded areas in an earlier slide, The dark areas are the sensitive habitat, but the areas to the east and north that were light gray were grasslands and weeds. A concern was that as we constructed roadways into the habitat area to install wells, that those roadways would then provide a pathway for wind to blow non-native seeds and establish weeds within the habitat area. Concern being that these weeds would then snuff out and overrun the protected plants. So UCSC staff worked with us for several years under subcontract to HGL to perform site-specific weed control at areas that they felt were most sensitive. That worked out very well, those guys being the experts in the area itself, and they knew right where to focus their efforts. We also embarked on two types of optimization. We'll call it qualitative. It's more typical of what many of us listening on the call have performed routinely, and more rigorous computational optimization. For the qualitative side, that involved performance monitoring, looking at trend evaluations on the monitoring well and performance well data, and then engineering judgment as to how you interpreted or what you did in reacting to that data and determinations, and groundwater modeling with our three-dimensional model of the groundwater plume. The graph on the right illustrates a little bit of this. This is the influent concentration to the treatment plant we constructed on the northwest boundary. When we started in July 2006, of course, with those 4 wells on the boundary, we had some high spikes coming in that rather rapidly dropped off. This big spike then in 2007 reflects the additional 4 monitoring extraction wells that we constructed along the axis of plume migration. And as we went forward, you could see that over time, there was a pretty steady and rapid decrease. One of our qualitative options there was, as I mentioned earlier, we took that monitoring well that you saw down the bottom of the initial pipeline, IW10, and thought that if we converted that into an extraction well, we could accelerate cleanup and improve performance. And this little upward rise that you see here in the influent concentration reflects the action of IW10. Along about this time, we were looking at better ways to accelerate and reduce our costs on the cleanup. We had a lot of cost surprises, as you might imagine, from the earlier plume extent being discovered. And we looked to our computational optimization effort. HGL has been working for the past decade closely on developing better optimization tools. And the physics-based management optimization, and I'll definitely call that PBMO in the future, was started back at that time. Fort Ord was the first ongoing project where we actually applied our technology as it existed then to try and improve our performance. And as Bert mentioned earlier, that is a model that also received a grand prize this year from AAES in the research category. So this slide illustrates the plume in 2006, and you can see the plume there in 2011 as we started thinking about using PBMO. So our qualitative optimization, it had some significant successes. We've been able to shrink the plume footprint by approximately half. We had reduced our annual sampling from 240 samples down to 70 samples. Part of that was shutting off wells as capture zones within them showed clean, working with the closure team, the agencies, to change the sample frequency. We've been able to take our peak pumping from around 120 gallons per minute to as low as 56 gallons per minute in some periods, and reduce the plume footprint by 50%. And part of that, again, being attributed to converting that one monitoring well to the extraction well. And at that point, let me turn it over to Dr. Govanesson, who will talk about the application of PBMO.
Thank you, Roy. Now I'll get into the computational aspects of optimization. We used PBMO to improve on the remedial design and operation at the site. Now let me give you some background on PBMO. PBMO is conceptualized as a medallion with 2 complementary halves. The lower half consists of site-specific calibrated flow and transport models. And the top half contains optimizer module comprising a suite of select optimization algorithms We used graphical user interfaces to facilitate preparation of input for the models. And we use OUI, or optimization user interface, to define optimization problems and to incorporate input from stakeholders. Now, a user sitting at the terminal can upload the instructions from the OUI and model files to PBMO, which resides on the cloud. PBMO then dispatches or distributes all the scenario-specific simulations to a number of available CPUs or central processing units. Now, during the run, the user can monitor the progress of the run using a dashboard on the terminal or mobile devices, for example, tablets or smartphones. The upper half of the medallion contains optimizer module or a number of select optimization algorithms. There are three key elements in optimization. Objective functions. These are the values that you want to maximize, for example, extracted rate, or minimize, for example, extraction rates and locations. The decision variables. These are aspects of the problems that can be varied. For example, rates and locations of extraction. Constraints. These are aspects of the problems that cannot be violated. For example, treatment capacity. On the left is an example of an objective function. For example, extracted rate, which you want to maximize as a function of extraction rates at 2 extraction wells. As you can see, there's several peaks, but there's only the one highest peak, which is kind of equivalent to Mount Everest. PBMO uses strategic search to determine the locations of the highest peak of Mount Everest. This is a plan view of the flow and transport model of the site. In the middle, right here, is the area of interest. So you can see that the digitization is the finest. The purple contour represents the extent of the TCE plume in 2005. The blue contours right here represent the outline of the carbon tetrachloride plume that Roy just talked about a few minutes ago. The model itself is three-dimensional with 4 layers to provide adequate vertical resolution. It has more than 50,000 cells, and this model kind of constitutes the low half of the medallion. Okay, the optimization is based on an existing flow and transport model, which is also based on our ModFlow and Surfact code. The objective of the optimization is to minimize cost to reduce TCE concentration to below 5 ppb through our OU1. There are 2 sets of decision variables: pumping schedule and rate at each well, and treated water injection rate at each well. Now, there are a number of constraints. The first 4 have something to do with the pumping and injection conditions. For example, we needed constant pumping along the boundary to satisfy regulatory requirements. We have a pumping cap, and new wells could not be installed in certain cells because of habitat protection constraints, because the treatment capacity is 200 GPM, so the total maximum cannot exceed 200 GPM. And last but not least is that the nearby carbon tetrachloride plume cannot be impacted. Now, as I said earlier, you can monitor the progress of the run, and this is an extract from the project dashboard. what you see is a plot of remedy cost that you want to minimize versus model scenario. Now, the results return to the dashboard in batches. So what you see is a snapshot of the second batch, and as you know, this curve also evolves with time. It just happens that at the end of the second batch, you have the optimal solution right here. We began the optimization with this amount, $661,000. This is based on an assumption that we let remedy in place run its course to completion. Now, the optimal solution is $172,000. That's equivalent to a savings of $489,000. That was obtained after 2 batches, 60 scenarios, and 70 minutes of CPU time on the cloud. Now, if you were to run all the simulations using one single PC, that would take about 3 hours. That's still considered practical, but in some cases, we have cases which may take days with single computer. So with the cloud-based PBMO, that would reduce the runtime down to minutes or a few hours. For additional information relating to the PBMO in terms of video clips or animations, go to our website and search for the word animations. Now I'd like to show the evolution of the TCE plume. The blue area represents the area of interest. The flow is from southeast to northwest, and this is the site boundary. Now, these red contours depict the outline of the TCE plume above 5 ppb in 2011. And this green patch represents the farthest area that the plume migrated to. Within the blue area, at the completion of cleanup, all the TCE concentrations below 5 ppb throughout the blue area. The reduction in cost was achieved by stopping pumping at all interior wells and maintaining boundary pumping to satisfy regulatory constraints. Now, the total pumping was reduced from 56 GPM down to about 10.7 GPM. And the cost was further reduced by identifying time to switch from pump and treat to monitored natural attenuation, and by reducing long-term monitoring samples from 70 to 26. As a side benefit, carbon dioxide emission was also reduced by 59,000 pounds per year. PBMO was also able to optimize the trade-off between longer cleanup time versus low cost. On the right is a plot of maximum concentration versus time. You can see that if we were to let remedy in place, which is shown in blue, run its course, the cleanup would be achieved by 2017. And PBMO sort of extended the cleanup time by a little bit, by 1 or 2 years, still within the time that's allowed by the record of decision. That doesn't violate the requirements within the record of decision. So the total cost savings amount to $489,000. And this is the breakdown of the savings. This is a comparison between remedy in place and cloud-based PBMO designs. You can see that most of the savings come from the saving in utility costs and saving in the O&M costs, and as well as savings in the sampling cost. And the total savings amount to $489,000. At this point, I'd like to turn over to Roy Evans, who will talk about exit strategy and site closure.
Thanks, Bill. Well, it's safe to say that when we started PBMO, I didn't expect to get an answer that said turn everything off, but that did prove to be acceptable to the regulators. We negotiated with the Army and the closure team, and it was agreed that that would be the case as long as we kept the boundary well pumping to be sure the public was confident that no plume was escaping off-site. So we continued our monitoring the situation and running the wells, and then kind of reverted back to qualitative optimization. As it approached the end of 2012, we realized that there were only 2 wells that still exceeded the overall cleanup target. And one of those wells was only very close to an idle extraction well. So we turned that pumping well back on, and by September of 2014, we had hit the cleanup targets that were specified in the ROD. So everybody was quite happy. We went to the EPA, and then you may recall that that little devil in the weeds back there at PFOA and PFOS. Now it's 2015, and that's a big issue. As you know from paying attention to the news lately, there are numerous places around the country that have been impacted by PFOA and PFOS. So the agencies said, well, no, we don't want to go straight to closure. We'd like the attainment monitoring program to incorporate some monitoring for PHA and PFOs, A and PFOS. So we worked with them to develop an exit strategy, and we used a screening criteria. At the time, the preliminary health advisories that were established by EPA for PFOA and PFOS were 400, 200 nanograms per liter. So it was agreed that we would incorporate that into our monitoring program and see where we stood at the end of the 2015. Well, sure enough, we did our 4 samples over the course of 2015. We had PFOA appear in all the wells. PFOA not being surprising because that's part of the key component of the AFFF firefighting foam that was used in the training exercises at the fire training area. Now we had PFOS though only in 2 wells, but they were well below this 400 and 200 nanogram per liter standards that were established in the PHA. So early in 2016, February of 2016, the agencies agreed that we could proceed to closure. But then came May of 2016, and EPA came out with a new health advisory, which lowered those previous limits from 400 and 200 nanograms per liter respectively down to a total of only 70. And now we are back a little bit in the weeds because 2 of the wells in the central part of the plume had exceeded that 70 nanograms per liter. So the Army and HGL got together. We worked out a rationale to extend that exit strategy and explained back to the agencies that the data showed several things. One, there was no further contribution from the source area. You may recall that in 1987, all the contaminated soils were removed. The upgradient wells closest to the former source area during the attainment monitoring were all non-detect for both compounds. Our off-site migration at the boundary was only total 4 nanograms per liter. So it was pretty clear that there was no new material coming, no high concentrations were leaving the site, and the 2 wells that did show contamination of PFOA above the standard were in the central part of the plume. The 4 attainment monitoring efforts that underway showed a mild but decreasing trend throughout for those concentrations. And perhaps most important of all, their operable Unit 1 lies within a groundwater exclusion zone established by the Monterey County Health Department. They're responsible for issuing permits for any new wells to be used for public consumption. And as a good chunk of Fort Ord is still undergoing groundwater cleanup, that exclusion zone extends not only to OU1 but elsewhere in Fort Ord. So there's no human health exposure pathway in place for drinking that water, even if somebody wanted to try and put a well in there. So in February of this year, the agencies reconsidered and once again said that OU1 was good to go. So closures in progress. In July of this year, we destroyed, properly abandoned all the OU1 wells. We decommissioned the treatment plant on the northwest boundary. We had earlier removed the old treatment plant in the source area. We had no evidence of adverse impact in the FNR to the rare plants. We conducted annual rare plant population surveys, much like the pre-construction surveys, every year throughout, and in the compliance with the biological opinions as well at each well site for 3 years after any intrusive activity there. And those surveys to date, in conjunction with the natural resource projection measures we'd undertaken, have not shown any significant impacts or adverse impacts to the rare plants within the FLNR. So at this point, the draft closure report has been written. It's in regulatory review. Comments, in fact, are due this Friday from the agencies on that, although we've already heard from the Department of Toxic Substances Control, who has said they have no comments on the draft closure report and they're ready to proceed to closure. For this work, we got ratings from the Army on our project task orders. This overall work was conducted under 2 separate contracts encompassing 7 task orders. 2 of those task orders are still open and 1 just recently closed, but we received performance ratings from the Army in 6 categories each on the 4 task orders that we've completed. So out of possible 24 ratings, we received 22 exceptionals and 2 very goods. We also received a nice letter of commendation from the Regional Water Quality Control Board for our efforts, along with the closure team, in getting OU1 to closure. Overall, looking back, some of the key elements of success on this project were an integrated approach. We kept in mind the habitat factors and the rare plant design issues throughout, both in design, construction, and in operation. Using optimization, both qualitative and computational, was key. That's a combination both of site expertise, if you will, on the qualitative side, and then the rigorous computing methods within PBMO for the computational. And teamwork and communication throughout. All the agencies and the University of California and the Army and the BRAC office and HGL really had a common goal that we adhered to throughout all the ups and downs of this project, and that was to keep moving forward, get the site cleaned up, and stay within the protectiveness requirements that everybody wanted for the public and the environment. And everybody really worked tirelessly towards that goal and cooperatively. Adaptability, I'm sure all of you have experienced this on other sites as you've worked in that. You just have to kind of roll with the punches as you discover things in the field. We kept implementing field procedures to protect plants and habitat. Converted that one well there back in 2010 to an extraction well when it was formerly a monitoring well. Developed the exit strategy and just keep looking at the data all the time and thinking about ways to fine-tune and tweak the performance. Optimization, again, is a critical thing. In order to, it's crucial in a performance-based remediation contract to use optimization in order to meet your performance goals and minimize costs. And the mix between back and forth between the rigorous and the site matter expertise, if you will, and the qualitative was key. PBMO, just as I mentioned, can be used with any physics-based model. It's set up right now easily to work with mud flow and mud flow derivatives, but it's also been used with surface water models or anything else that's physics-based. It's an extremely efficient tool in cloud computing. It's really revolutionized things at how many different runs you can make. So with that, I once again appreciate AES's recognition and opportunity in presenting this, and would like to turn it back to Burke and open it up for questions.
Well, thank you for sharing all that content with us. An amazing project, an amazing part of the country. We do have the ability to do questions and answers, and so far I don't think I'm seeing any questions. You've done a great job of explaining it all.
Well, good. Did we lose audio at any point throughout there?
No, not on my end.
Okay.
Q&A window says some people lost audio, but it came back since. Question from Steve Rose. What was the resolution for the off-site plume?
Oh, thank you. I meant to mention that. Fortunately, the Army, we discovered the off-site plume must have been pretty quickly after it had actually migrated off-site, because it was only probably 700 to 900 feet in length and relatively low concentrations. The Army, under separate contract, established a quick 2-extraction well carbon treatment system, and they were able to reach cleanup on that plume within 2 years. And they got to that point in 2009.
How much did it cost to set up, perform, and interpret the PBMO runs?
The cost of setup. Right now, it depends on the environment. We don't have an exact, we cannot quote exactly right now, but it depends on the environment. It depends on the size of the problem. It depends on how would you like it to run based on the certain preference. So, but what I can say is that the cost is reasonable, but we cannot give you the exact quote right now.
And this is Roy. Let me just back. Jewel was referring somewhat to more current times. This, as I mentioned earlier, was the first time we tried PBMO on a project. We had not yet set it up on a cloud platform. It took us, we spent roughly around $40,000 on that effort. These days, if you wanted to do something with PBMO, depending on the complexity of your project, you're probably in the $50,000 to $100,000 range.
Okay. Another question from Moses. I assume that the PFOA/PFOS contamination to the water came from leachate, from contaminated soil. How was the soil remediated?
The soil was, this was before our time. They excavated the soils back in 1987. They took them down to a maximum depth of 31 feet. They lifted them. They used biotreatment piles to remediate the contaminations in there. Now, again, this was 1987. They weren't even looking for PFOA, PFOS, but they did use that to remediate all of the VOCs that were the known site contaminants. It took about 4 years for the soil piles to meet the soil cleanup standards, and after that it was used as borrow for fill in construction activities.
Just a question from me. Knowing that you guys are right there next door to Monterey and some highly sensitive tourist areas, was there a lot of work going on with the local community, the Chamber of Commerce, and whatever else? What you guys were doing was properly, I should say, familiarized with the local population?
I can give you some background on that. Bill, if you want to weigh in when I'm done, please feel free. But particularly early on when the plume went across, discovered the plume was going across the boundary, there were community presentations. The Army does a good job every year. There's a couple open houses that they hold for the public on all the operable units and groundwater cleanup with site tours for the public. And they've been heavily involved in keeping the public informed.
That was a good idea.
Yeah, I think I can add a couple more things. Because this is a Superfund site, the public involvement process is a very important part of our decision-making process. So every time there's a record of decision, where there's a proposed plan that goes out to the public, and we have specific meetings on that proposed plan, and we've accommodated that for both the OU1 that included the offsite.
Did the public appreciate the fact that what you were doing was sort of, pardon the term, groundbreaking? That by applying the new technology, you're able to do a lot more with a lot less and do a better job of it?
Normally,
I don't think I ever heard anything from the public in that regard, except thanks for getting cleanup done.
Yeah.
Perhaps I can say something on the return on investment of PBMO. You can see that the return on investment of PMO is at the order of 7 to 10 because the savings is close to $500,000, while this expenditure was only $50K.
Yeah. So that's, like you say, a substantial change. Sounds like pretty good ROI there as well. Okay, well, last call for other questions to our audience. If not, we'll call the session closed. Thank everyone for coming. And feel free to contact us if you have any questions, or contact our speakers, because they're more than happy to talk to you about what they did and how it might apply to where you are.